Okay, so another topic we have to deal with when it comes to Lewis structures is formal charges. Now, formal charges, it's kind of a concept that you don't really have to know what it means necessarily, but the most important thing is knowing that it's functional purpose. So essentially, the charge of any atom, if an atom has the same electronegativity, if in the molecules, if all of them have the same electronegativity, honestly, I don't really know what that means or how that really helps. But the main thing you need to know is that when you draw Lewis structures, sometimes you can have multiple legitimate possibilities of distributing electrons. So it actually works. Whatever it is that you draw, you can have more than one way of basically making a correct-ish Lewis structure. But there can only be one, maybe even a second one, that can have the favorable arrangement. Not all of them will work. Not all of them, at least, are what's considered to be accepted. Now, how do we decide what's accepted or not? Let's go and take a look, first of all, at how we calculate formal charge. So formal charge in this example is going to use cyanide ion, and to calculate it, all you have to do is take the assigned electrons and subtract it from the valence electrons. I'm giving you a little formula here where the formal charge, Fc, is equal to valence electrons minus assigned electrons. Just so you know, assigned electrons is actually the electrons in lone pairs, so all of the electrons in lone pairs, and half of the bonding electrons in a single atom. Let's go and see how this works for carbon and nitrogen in the cyanide ion. So with carbon over here, we'll start with this one. Carbon, to get the formal charge is equal to my valence electrons, which is 4 for carbon, minus the assigned electrons, which is going to be 5, because you have the 2 here in the lone pair and 3 bonds, but there's 6 electrons in there. So we'll take half of those 6 electrons and get 3 one more time. So we have, again, the 2 here and the 3 electrons for carbon. That makes this, again, a total of 5. That'll give you a formal charge of -1. Okay. Now I know it's kind of confusing dealing with the bonds versus the electrons that are assigned to it, and to be frank, I'm not a huge fan of either. But just recognize that you have the bonds here that can count for 1 electron specifically for just carbon. Nitrogen kind of follows the same principle here. You start off by calculating the number of valence electrons, which is 5, and you subtract the number of electrons assigned to it. So right here you have 2 electrons, and it's going to be 1, 2, 3 more electrons assigned just to nitrogen. So that's going to be a total of 5 as well. So that means your formal charge on nitrogen is 0. So what exactly can you do with this information? Well, for now, not a whole lot, but I just need you to be able to understand how to calculate it. One more thing you need to know is that anytime you have formal charges, the sum must equal to the charge of the overall molecule. So -1 plus 0 is also -1 for the entire molecule. Applying the formal charge. Well, let's go and try this out. So you have 2 alternative structures that are completely legitimate for carbon dioxide. Now, you might have your own preference for which one you like. For example, the one on the left looks more interesting because it's more symmetric, or the one on the right you think is correct because it's got some triple bonds. And triple bonds, when we see them, it's kind of interesting. Well, unfortunately, just using the eye test isn't going to be sufficient here. So you actually have to go through and look at the formal charges for both of them. Now, again, when you look at this formal charges, the work has kind of been done for you here. But when you look at the formal charges here, the one on the left has pretty much all zeros, right? So 6 electrons minus 6 electrons also gets you 0 for across all these here. For the second structure, though, you can see that it's a -1 versus a +1. Right? So this is how you calculate formal charges for either of these structures. Now, how exactly do you know which one is better? What is the observed structure that is seen experimentally? Well, this is kind of the breakdown. So when you apply formal charges, you should just be able to see that you have the 6s, the 4s, 6, whatever, and these are all zeros, and these are all -1s and +1s. As it turns out, atoms should have formal charges as close as possible to 0, and this is desired. So having as close to 0 as possible is better. So already you can see that the one on the left is your favorite structure, at least is the more important structure. And in case this also comes down to it, if it comes down to having the lowest charges possible, the negative formal charges should be assigned to the more electronegative atoms. So again, you have to know your trends. You should be able to realize which one's your your more electronegative atom, and that will want to take on the negative charge. Makes sense, right? It draws electrons towards itself. On a final note, make sure you know that formal charges are not the same thing as actual charges. There's a whole complicated system of relationships that we're not concerned with in this class. Just know that, again, formal charges, actual charges, a little bit different. Practice. So using the thiocyanate ion, I'd like for you to go ahead and determine the formal charges of the three possible Lewis structures, all of which are completely legitimate and work out, and also then determine the preferred Lewis structure by looking at their formal charges. All right, so go and pause for a moment. I'll let you go ahead and take a second here and try these out yourself, and then we'll pick up where you have left off. Now that you've figured out the structures, let's go and see what they're supposed to look like. So these are the three potential structures that you're supposed to have. Now, again, all three of these, it's kind of hard to know which one's the best and which one's not the best. Again, the eye test doesn't really help us out here a whole lot. So you have to rely on formal charges. So go ahead and take a second. If you couldn't figure out the Lewis structures earlier, go and take a second, pause the video, and see if you can figure out the formal charges here. Okay, so hopefully you've also figured these out. The formal charges end up being these. So the one on the left, center, middle, you have their assigned ones, and there you go. All right, so hopefully you recognize that from the previous rules, which one of these are probably the most important. Well, you can go ahead and rule out the one on the left entirely, because this one is the furthest away from zeros. Notice you have a -2 and a 1 right here, whereas this one has a 1 and a bunch of zeros, while this one also has a bunch of zeros and 1s. So this one I can go ahead and ignore. Right? That's not an important structure. So it comes down to these two. Right? So which one is going to be the winner? Well, if you go ahead and kind of sort of use your electronegativity vibe here and kind of pick up which one is the more electronegative one, turns out nitrogen is the more electronegative one. So with that information, which one should be the more important structure? It should be the middle one. So this one right here ends up being the most important one. Let's go and try another one. Right, this one's called this is the cyanate ion. On the previous example, I didn't really tell you what the formula was, but hopefully you went up and found what thiocyanate was. In this case, I'll go and tell you what it is. A cyanate ion, this is actually a CNO minus. All right, so again, with this information, go ahead and take a minute, figure out which one is the most important structure, and then you'll be able to answer the question. Okay, so it looks like I made a bit of a boo-boo, actually. It turns out that it's not cyanate, it's CNO. It's actually going to be the formula NCO. That's a -1 charge. Okay, and it looks like we are looking at this with the correct answers here. So based on what we have, you should be able to see that the only one that works, or the one that works best anyway, is this one on the far left, where you have the oxygen that is singly bonded and the nitrogen that is triply bonded to carbon, and that again maximizes minimizes the values and also puts the most electronegative atom with the charge. Great. Finishes off, let's talk about resonance structures. Resonance structures are very similar in some ways to Lewis structures. This does involve multiple structures, but only, again, the correct one. So variations on just the correct structure. So let's go and take a look. First of all, what about ozone? First of all, you should know that ozone is O3. So you see ozone right here with a double bond and a single bond. Now, again, most of us can probably look at this and not think twice about it, but actually, wouldn't you expect those to be different, those two bonds? One expectation is that a single OO bond is actually a different length than the double OO bond. It'd be predicted that the single bond would be longer and that the double bond is shorter. And this is kind of a truth that applies to just about any bond out there. Single bonds typically are longer, whereas the double bonds are shorter. However, when it comes down to it, the experimentation shows that bond lengths are actually identical. In fact, the single bond and the double bond between those two different bonds, they actually end up being the exact same length. So this side over here and this side over here don't actually have, one longer, one shorter. What exactly is the explanation for this? So you can see here that the markings are there. This one says that this is a certain length, this one says a certain length, and they're reported in angstroms. What exactly explains this? Why does this happen? Of course, you can probably see where this is going. Resonance is the key here. So resonance actually comes down to this. Right here, you have two different resonance structures. Before, we put the double bond on the left side or the right side. Now we have on the left side. Over here, the double bond is now moved to the right side. Both of these are identical. Both of these structures are exactly identical. And depending on what you feel like doing that day, you could have put the double bond on the left side or the right side. So these are what we call resonance structures. They're alternative, completely equivalent Lewis structures, but the electrons are simply placed differently. Now, of course, this is different than Lewis structure, sorry, than formal charges, because every single one of these has the same formal charge and doesn't have any sort of difference, and there's no more favored one. Right? Overall, again, they'd have the least number of values, so they're all really close to zero, and that the most electronegative has the charge. Then that means both structures contribute equally to the observed structures and properties of ozone. So that means no one of these is actually observed. They both kind of are an average, or they get averaged into the actual structure of ozone. Now, actually representing ozone is a little bit more difficult, at least in terms of what we see with bonding. But just be able to picture this as sort of a merging of the two, an average of the two. Bond character. So it's not really a single bond between oxygen and oxygen here. And it's not really a double bond. So the oxygen-oxygen bond in ozone is kind of like a 1.5 bond. You can't really say it's a single or a double because it actually is somewhere in between. Now, to kind of picture that, let me give you an analogy. First of all, let's go ahead and look on the left side with our primary colors. Blue and yellow make green. That's nothing new. Blue is its own identity. Yellow has its own identity. But when it's mixed together, it makes green, which again is its own identity. So green, again, is an average of the two. But you should also recognize that it's not like green sometimes is blue and sometimes is yellow to make green. No, green is green. So the same way, the ozone molecule isn't sometimes where the resonance structure has a double bond on the left and sometimes has a double bond on the right. No, in fact, it kind of has both of them together at the same time, therefore has its own identity. So the resonance structures here contribute to the average of the ozone molecule. Let's go and try nitrate. All right, nitrate here, I want you to try this out. Nitrate, you should know that as a polyatomic ion, and describe its bond character when you draw out the resonance structures for nitrate. All right, take a second and try and do this one on your own. Now, let's go ahead and take a look at the actual structures. So this one is going to be kind of diagramming out what it's supposed to be. Notice that you have these sort of double-sided arrows. These double-sided arrows just basically represent the resonance structures, and this is scientifically correct to use those double-sided arrows. So when you're drawing different Lewis structures of resonance structures, please make sure you include that to know that there's no reaction going on. So single-sided arrow is not correct. Also notice that it's got the brackets and the minus charge around the outside. So yeah, if you look at it, it kind of just cycles through. All three of these are completely the same. If I just rotated it around, you'd basically see the same structure. And so all three are resonance structures. In terms of its bond character, how would you maybe characterize that? Well, it'd probably be longer than a single bond since there is a double bond that's being passed around. But it wouldn't quite be a double bond since it's diluted down with other single bonds. So if I kind of averaged these, some of you might be able to figure out or kind of theorize or at least hypothesize. It's kind of like a 4/3 or like a 1 1/3 of a bond kind of here between my NO. So my NO bond for nitrate, you wouldn't just say it's a single or a double. You'd say it's about 1 1/3. And that's the best way to approximate what it's like. Looking at these here, you have sulfur-oxygen bonds. Which one would you expect it to be shorter? Would it be the SO3 or the sulfite, which is on the top? Now, if you kind of look at this, sulfite, which is on the bottom. Sulfite, again, has pretty rigid single bonds all the way around. So the sulfite on the bottom would not be expected to have any sort of shared bonding. Right? Whatever you see is what you get. Whereas up here with my sulfur trioxide, that double bond is actually passed around. So you kind of have an average. You kind of have a chance to average out all of your bonds. So in terms of which one has a different character, the sulfur trioxide kind of has, again, sort of like a 4/3 or 1 1/3, 1.333 kind of bond. Since it has a little bit higher bond character, that means the one that'll be shorter will be the sulfur trioxide, because if it's a higher bond order. The bottom one, the sulfite, that one's going to have a lower bond order, therefore it's going to be longer. Benzene, hopefully most of you can kind of at least recognize benzene. It's actually got a long historical importance here, and you can kind of look into where it's used, and it's such a commonly used structure that it's actually worth looking into. Benzene is a ring structure of the formula C6H6. And it looks like that. So if you kind of look at the structure here, you notice it's got a ring of C's, and then it has H's coming off of each of them. But it also illustrates resonance too, because, well, if you put it in these spots, you could hello. Okay. well, we'll kind of leave that there for now. But if you leave that and leave these here in these spots, you also know that they kind of can be moved around and shifted here. So this one then shifts here, and this one then shifts there. So then you have, again, the same thing, but the electrons are in different places. So this is what we kind of call resonance structures. These, again, have such a different and unique pattern that you actually call them, or actually have different ways of representing them. So here, benzene can also be shortened to have this sort of just stick